Hello everyone. In this video, we will learn to 1. Calculate the formal charges, 2. Differentiate between equivalent and non-equivalent resonance structures, 3. Compare the significance of contribution to the resonance hybrid of possible resonance structures. The resonance structures that we have drawn for molecule ozone and carbonate ion in the previous video are called as equivalent resonance structures. Equivalent resonance structures have same distribution of formal charges, while the non-equivalent structures have different distribution. First, let us define what formal charges are and how we determine the formal charges of an atom before looking at the distribution. The formal charge, Fc, is the charge assigned to an atom in a molecule, assuming that electrons in all the bonds are shared equally between atoms, irrespective of differences in the electronegativity values. I'm going to repeat this again. We have to assume that electrons in all the bonds are shared equally between atoms. The formal charge of an atom is equal to the number of valence electrons in a free atom minus number of valence electron in a bonded atom. We are assuming that all the bonds are equally shared between atoms. Therefore, the number of valence electrons in a bonded atom is equal to total number of non-bonding electrons plus half of the number of bonding electrons. Since the bonding electrons are equally shared, each of the bonding atom gets one electron. Let us do a couple of examples. Calculate the formal charges of both the chlorine atoms on the chlorine molecule. First, let us draw the Lewis dot structure of chlorine molecule. Then let us calculate the formal charge of each of the chlorine atoms. According to the formula, the formal charge of an atom is equal to the number of valence electrons in a free atom. That is, the chlorine atom in its free state or non-bonded state. As we know, chlorine atom belongs to group 7a, therefore it has 7 valence electrons in its free state. Now let us move to the second part of the formula. That is, count the number of non-bonding electrons. For chlorine atom on the left, there are 6 non-bonding electrons. Now we count the bonding electrons. Chlorine atom forms one bond, that means 2 bonding electrons. Since we are assuming that all the covalent bonds are equally shared, the number of electrons the left chlorine atom gets is equal to half of the total number of bonding electrons. That is, half of 2, which is equals to 1. So overall, it is 7 minus 6 plus 1, which comes out to be 0. And we can do the same thing for chlorine on the right. It also comes out to be 7 minus 6 plus 1, that's 0. There is an easier way to calculate the formal charges. Whenever you are given a molecule, break all the bonds in the molecule, and for every bond you break, give 1 electron each to both of the bonding atoms. Now count the total number of electrons around each atom. That would give the total number of valence electrons in a bonded atom. And you subtract that number from the total number of valence electrons in a free atom to get the formal charge. For any molecule or ion, sum of the formal charges on all the atoms is equal to overall charge on the molecule or ion. Therefore, one way to verify if the formal charges you calculated are correct or not is to add up the formal charges on all the atoms and it should give you the overall charge on the molecule or ion. For chlorine, the formal charges on each of the chlorine atoms adds up to 0, which is the overall charge of chlorine molecule. Now let us calculate the formal charges of all the atoms in the two resonance structures of ozone molecule to classify them as equivalent or non-equivalent resonance structures. We have already drawn the resonance structures of ozone in the previous video. I'm going to use the same resonance structures here. Now let us calculate the formal charges of each of the oxygen atoms in both the resonance structures. Just to recall, formal charge is equal to the number of valence electrons in a free atom minus number of valence electrons in a bonded atom. Oxygen belongs to group 6A, therefore it has 6 valence electrons in its free state or non-bonded state. Now what I'm going to do is break all the bonds in each of the resonance structures, and whenever I am breaking a bond, I am going to assign 1 electron each to both the bonding atoms. For oxygen A on the left here, the number of electrons in a free atom is 6, and I have 6 electrons around this in the bonded state. The formal charge therefore is equal to 6 minus 6, that is 0. For oxygen B, the total number of electrons in a free atom does not change, that is 6, but the number of valence electrons in the bonded state are 5. So 6 minus 5, you get plus 1. And for oxygen C, we get 6 minus 7, that would give me minus 1. Similarly, we can calculate the formal charges of 3 oxygens on the other resonance structure as well. For each of the resonance structures, the formal charges add up to 0, which is the overall charge on the molecule. So that tells us we calculated it right. Now, if you look at the distribution of the formal charges on both the resonance structures, there are 3 oxygens, and one of them have a formal charge of 0, and the second one has a formal charge of 1, and the third one has a formal charge of minus 1. We can say this for both the resonance structures. These types of resonance structures, that is, resonance structures with same distribution of formal charges, are called as equivalent resonance structures. Let us do another example. Draw the resonance structures of nitrate ion and determine if the resonance structures are equivalent or non-equivalent. So we follow the guidelines of Lewis dot structures first. Place the least electronegative atom, that is nitrogen, in the middle, oxygens on the sides, count the total number of valence electrons, connect the terminal atoms to the central atom by a single bond, subtract the used up electrons, and place the remaining electrons on the terminal atom first, and if there are any leftover electrons, we place them on the central atom. But we used up all the electrons. Now let's verify if each of the participating atoms has an octet configuration. The 3 terminal oxygens have octet. However, the central atom, which is the nitrogen, is 2 electrons short of octet. So we need to transfer a lone pair from one of the terminal atoms as a multiple bond to increase the valence electrons in the central atom. Now, which oxygen I should use to transfer this electron pair? There are 3 possibilities. Therefore, I get 3 resonance structures. When I move electron pair from oxygen 1, I get one structure. When I move electron pair from oxygen 2, I get the second resonance structure. And when I move electron pair from oxygen 3, I get the third resonance structure. Now, in order to calculate the formal charges, I am going to break all the bonds in each of the resonance structures, and whenever I break a bond, I assign one electron each for both the participating atoms, and then calculate the formal charges, which is the total number of valence electrons in the free atom minus the number of valence electrons in the bonded atom, that is, the number of dots around each of the atom. Now these are the formal charges for all the atoms in all the resonance structures. If we add up the formal charges of all the atoms in a particular structure, they will add up to -1, which is the overall charge on the nitrate ion. If we look at the distribution of formal charges, nitrogen has a formal charge of +1 in all three structures. One of the oxygens has 0 formal charge, and the remaining two oxygens has -1 formal charge. Therefore, we can say the distribution of formal charges is same and that these are equivalent resonance structures. Let us do another example. Draw the resonance structures of NCO- ion and determine if the resonance structures are equivalent or non-equivalent. Pause the video here and try to answer this question. Let us first draw the Lewis dot structures. The order in which the atoms are connected is already given, meaning carbon is the central atom. We put nitrogen on the left, oxygen on the right. Next, we count all the number of valence electrons, comes out to be 16. Connect the central atom to the terminal atoms by a single bond. Subtract the total number of electrons used. I have 12 leftover electrons. I'm going to place these electrons as lone pairs on the terminal atoms. Now I used up all the 12 electrons. Let's verify if each of the atoms has an octet configuration on the molecule. Both the terminal atoms are octet. The carbon in the middle needs 4 more electrons to attain octet configuration. That is 2 more electron pairs. There are 3 possibilities. The 2 electron pairs can both come from nitrogen. The 2 electron pairs can both come from oxygen, or one can come from nitrogen and the other can come from oxygen. These 3 are the resonance structures of NCO- ion. Now I'm going to calculate the formal charges. To do that, I'm going to break all the bonds in all the resonance structures, and whenever I break a bond, I assign 1 electron each to participating atoms. Nitrogen belongs to group 5A, so the number of valence electrons in its free state is 5, and I have 5 dots around nitrogen in this structure. So the formal charge is 5 minus 5, that is 0. Carbon has 4 valence electrons in its free state and 4 dots around it in this molecule. So 4 minus 4 is equals to 0. For oxygen, it is 6 minus 7, that would be -1. Let's go to the second structure. Nitrogen, 5 minus 6, that is -1. Carbon, 4 minus 4, that is 0. Oxygen, 6 minus 6, that is 0. Third structure, nitrogen, 5 minus 7, minus 2. Carbon, that is 4 minus 4, you get 0. And oxygen, 6 minus 5, that is plus 1. As we can see, the distribution of formal charges is completely different. Even though the carbon's formal charge is same on all the three structures, nitrogen and oxygen have three different formal charges in the three structures. Therefore, these type of resonance structures are examples of non-equivalent resonance structures. When a molecule is represented by two or more non-equivalent resonance structures, getting the structure of resonance hybrid is not as simple as taking the average of all non-equivalent resonance structures. The non-equivalent resonance structures do not equally contribute to the resonance hybrid. That is, some resonance structures are more representative of resonance hybrid than the others. In other words, some resonance structures contribute more to the resonance hybrid than others. Now the next question is, how can we pick the structure that best represents the resonance hybrid? We will discuss the criteria for this in the next slide. There are three important criteria that we follow which will help us pick the best non-equivalent resonance structure. 1. Smaller formal charges are more preferable to the larger ones. When I say formal charges, it is in terms of magnitude, not the number. That is, a -1 is more preferable than -2, and similarly, a +1 is more preferable than +2. The same non-zero formal charges on adjacent atoms are not preferred. That is, if we have negative charges on two adjacent atoms or positive charges on two adjacent atoms, the structure is not preferred. Third criteria, a more negative formal charge should reside on a more electronegative atom. Whenever you draw formal charges, you often end up getting negative formal charges on several different atoms. So let's just say in one structure you have a negative charge on carbon, and in other structure you have a negative charge on oxygen. The -1 charge on oxygen is more preferable because oxygen is more electronegative than carbon. Now let us use these criteria and pick the best non-equivalent resonance structure that best represents the experimental structure of NCO- or resonance hybrid of NCO- ion. Structure 1 and structure 2 have smaller formal charges than structure 3. So the structure 3 is not a good representation of the experimental structure. The structure 1 and 2 have same types of formal charges, that is -1, 0 and 0. However, for structure 1, the -1 formal charge is on oxygen, which is a more electronegative atom. Therefore, the structure 1 is the best representative of the experimental structure of NCO- ion. All three resonance structures contribute to the experimental structure or the structure of the resonance hybrid. However, it is not an equal contribution. Instead, it is a weighted average of the three structures. Structure 1 contributing more to the resonance hybrid, followed by structure 2, then structure 3, depending on the criteria that we discussed. Let us do one last example. Draw the resonance structures of SCN- ion and arrange the resonance structures in the decreasing order of their contribution to the resonance hybrid. Pause the video here and try to answer the question. Let us start by writing the Lewis dot structure. Sulfur and nitrogen on the side, carbon atom in the center. Count the total number of valence electrons. Connect the central atom to the terminal atoms by single bond. Use the remaining electrons to place on the terminal atoms. We used up all the electrons. Now verify if each of the atoms has octet configuration. The carbon in the middle does not have octet configuration and needs 4 more electrons to attain it. That is, needs 2 pairs of electrons. The 2 pairs of electrons can come in 3 different ways. Both of them from sulfur, both of them from nitrogen, one from sulfur and one from nitrogen. These are the resonance structures of SCN- ion. Now let's calculate the formal charges. I'm going to break all the bonds and assign 1 electron each to both the bonding atoms. For sulfur, it belongs to group 6, therefore it has 6 valence electrons in its free state, and I have 5 dots around it here. So it is 6 minus 5 plus 1. For carbon, group number 4, minus 4 dots, that is 0. Nitrogen, group number 5, minus 7 dots, that is minus 2. And then we move on to the second resonance structure and the third one. If we add up the formal charges on each of the atoms in a particular resonance structure, they add up to give the overall charge on the SCN- ion, which is -1. That tells us the formal charges that we calculated are correct. Now let us look which one contributes most to the resonance hybrid. As we can see, structure 1 has higher formal charges of -2 and +1. Therefore, it is not a good contributor to the resonance hybrid. The structure 2 and structure 3 have same distribution of formal charges, that is -1, 0 and 0. However, the structure 2 has negative formal charge on nitrogen, which is a more electronegative atom than sulfur in the structure 3. Therefore, structure 2 is a better structure or contributes more to the resonance hybrid. If I have to place these structures in the decreasing order of their contribution to the resonance hybrid, it would be structure 2 followed by 3 followed by 1.